In the last video, we covered how to make islands, mountains, rivers, and arch bridges. In this video, building on what we did last time, we'll dive into the terrain material system, the scatter system, suspension bridges, exporting the environment, and importing it into UE. Let's start with the terrain materials. The PSD to river node outputs two strings of data once calculated. The first one on the left outputs just the height field. The second port outputs data for scattering meshes along the river banks. We'll process the height field data from the first output so that it can support the terrain materials inside UE. There are three main nodes related to terrain materials. They are all located under QuickBrush Landscape Material tab. First is Set Layer Weight. This is where we set the weight value for each layer. The second one is the Get Layer Weight node. This extracts the layers we set and turns them into a mask. For example, if we need to plan specific scatter items on both sides of a road, we can use this to get that data. Then we have the Text Index Weight to Layer node. This converts materials recorded using ID indexing and weights into our actual 32 layers. This material system uses a blend layer approach. It uses for indices and for weights to record values for 32 layers, which really helps save memory. I'll just show you a quick example here, because the materials for the whole island are quite extensive. A simple demonstration of how the material system works should be enough to get the point across. Let's plug the debris into the mask and take a look. Create HeightField_remap node. The mask outputs values from 0 to 1. The mask inputs values from 0 to 4. Let's say this is the weight we want for one of our layers. Let's tweak this a bit and set this current value to the designated layer. Right now, the transition inside isn't very smooth, so let's give it a slight blur. Adding just a bit of blur here. ... will make the transition between material layers look much more natural. Next, we'll pipe this into a set node. Now information is displayed here. Before adding this node, it had 25 layers inside. After adding it, it adds another 8 layers, bringing the total to 33. With the addition of the 8 height-field layers for text index GBA and text weight GBA, the layers and weights for 32 materials are recorded. This drastically cuts down on memory usage and system load. However, it does have a downside. At any given single point or location, it can only record a maximum of 4 materials. You can't blend all 32 layers simultaneously on the exact same spot. Generally speaking, 4 layers are more than enough for a game. Once it's set, and we have those 8 extra layers, we can use Get Layer Weight to extract and check the data inside. For instance, if we set it on O1, then OO will have no data. But O1 will have data. We set the data on OO, so there is no data on O1. The rest of the data goes to 31. It automatically clamps the total weight of all layers to 1. Let's use the castle area as an example. Let's create a height-field copy layer node. Isolate CSTE. This is our castle area. Apply a mask to it. Now let's apply a set layer weight to it. Let's assign this one to layer O1, for instance. Now let's check it using Get Layer Weight. You'll notice that the weight inside layer O1 has been excluded. And what we're extracting in layer O1 is strictly the castle itself. In layer 31, it still filters out the material networks of all nodes outside the castle area. With this terrain material setup, you only need to think about what weight info you want to extract and set it to the designated layer. You don't have to worry about the overall weight balance. It always guarantees the total weight equals 1. Layer 1 contains the castle. There's still nothing in 2. Since we haven't assigned any values to it. I won't go through setting up every single remaining layer, because there are too many and it's just repetitive. No matter how many times you set it, it will always stick to these 8 layers to record the materials. You can set the same layer multiple times. For example, if I set a layer upstream, I can still set values for that same layer downstream without any conflicts. Once that's set up, use the text index weight to layer node. What this node does is convert the 8 layers of info we just set into a standard 30 true layer output for UE to use. If you're using UE's default material blend mode, you need to convert it into 30 true layers. This goes from layer 0 all the way to layer 31. Let's check pure layer here. This will wipe out any unused, useless layers, keeping only the material layers we actually need, along with the height-end mask. If the material inside UE uses the blend method, you'll need to call this node before exporting and set up your UE material here. Or your Unity material. For references, you generally want to check this pure layer option. For a detailed explanation, you can click on this little question mark to check the help documentation. For example, if we have a grass layer that needs grass or trees growing on it, we use getLayerWeight to pull out the specific layer we need. Like layer 00. We can use this layer for scattering. Let's do a quick scattering breakdown. Drop down the multi-scatter node. Create a scattering rule. If you don't specify a source here, it defaults to using the mask. If you do specify one, you will use that specific layer. Type in your UE reference path or Unity reference path right here. Checking scan means it will use a decal approach to control the object's rotation. Because decals behave differently than standard tree planting, this gives the decal support. This section controls the density distribution. We'll leave it as is for now, since this node natively uses the mask to directly control density. Here is the mask area. You can see the density is higher here, and lower over here. This density control relies on a distance value. Setting it to true means 1 point every 2 meters. If we bump it up to 10, the density will thin out. There are 2 modes here. The first is by count, and the second is by distance. By count works with clusters like how many items I want to plant within a cluster. Say you want to place a total of 10 assets within a certain area, just dial in that number, and it will scatter exactly 10 items in total. By distance, on the other hand, strictly regulates density, meaning in areas where the mask is 1, the density will match the specified value like 1 item every 10 meters. If the value is 5, it means 1 every 5 meters. The proxy here uses truncated cone data, utilizing two mathematical cones to find the intersection. Let's scale the values up a bit, giving it a base radius of 1, a top radius of 3, and a cone height of 3. This way, we can use it to visualize exactly where our planted assets are going and their general size. Even though you can't truly preview the actual asset data inside Houdini, as long as your input dimensions are fairly accurate, it gives a solid representation of the plan's scale and position. Over here is scale, which controls the scale variation or jitter, meaning it will randomly scale between 0.8 to 1.2 times the original size. Relax loosens up the spacing between points. It creates a bit of a mutual repulsion effect. Of course, if you want it to look completely natural, just turn this off. To avoid overlapping assets, we can check delete overlap. Any overlapping points will be discarded. Let's tweak the size of the plants. We're going to make them a bit larger. Set this to 6. Set this to 30. Let's lower the density a bit. Say we want to scatter some rocks around the base of the trees. There's a companion subsystem down here. This handles scattering specifically around the trees. It will restrict itself to the designated area. Let's set this to 5, for example. This value is 10. 5 to 10 meters. Whoops, that density is way too high. Now they only spawn around the tree within the specified radius. Let's say 5 to 7 meters. 数值为1。They will consistently stay within this distance range. It has its own overlap settings, still represented by the cones. Checking delete overlap will clear up any intersection issues. Since there are a ton of points here, and it's causing lag, let's turn off the companion scattering for now. Let's go over these parameters. RandomOp introduces some random tilt and lean to their orientations. This one handles rotation along the y-axis. This option allows you to knock them over. It's a randomized falling effect. They will always fall in line with the slope direction of the terrain. Of course, you can invert it to make them fall uphill. There's a value here if we check it. Let's set the density to 10 to make it a bit more spaced out. Oh, too big, let's do 5. Enabling this means it will try to recover as many deleted non-overlapping points as possible. If you're aiming for a high-density scatter, you definitely need this turned on. Let's say we set up another scatter rule for this zone. This is the second scattering rule for this specific area. This handles the larger, fallen tree we just looked at. The logic remains identical. Check delete overlap. With overlap deletion on, no extra assets scatter directly underneath the trees. The fallen tree area is excluded from scattering due to overlapping with the cone. This is just a case study. You can load the preset rule via template. For example, what kind of trees grow in my meadow biomes, and what their companion relationships look like. We can export this whole series of parameters we just tweaked into a JSON file. Then, when you need it elsewhere, you can just load the JSON file back in via the template method. Once loaded, it repopulates these fields with the saved data, making it reusable. If you have a massive amount of scattering rules, it might occasionally fail to refresh. Just click this refresh button to force a manual update. That's the gist of the parameters. If you want a deeper dive, check out the help docs here. Now, let's take a look at the grass scattering rules I set up earlier for Skull Island. Let's use a template to load that specific JSON file. This is the one I saved before. Let's load it up. Awesome, it's loaded. This flat thing lying on the ground down here is a decal. Every large tree has a decal beneath it. The first scatter rule is for a fairly large tree, about 12 meters tall. It has a decal attached right underneath it. These are 2 decal paths. You can have it randomly pick one. The scattering along the riverbanks actually uses this exact same built-in logic. Let's add a label to this. This one is terrain material. Let's label this side too. Ecosystem scatter. Next up, let's look at how the suspension bridge is made. First, let's draw a curve. Create a suspension bridge node. This parameter controls the width of the bridge. This controls the spacing between bridge towers. A larger value means fewer towers. The tension between the upper and lower cables is different to make the simulation look more realistic. We control that right here. There are two modes here. One is driven purely by height. Let's beef up this line thickness first so you can see it clearly. Let's set this value to 5. This controls the number of horizontal ropes running underneath the bridge deck and the vertical gap between them. This is where you specify the UE or unity material. Different slots call in different assets. This is the curve tool you use for the bridge planks. Let's set one up. Say the bridge is 8 meters wide. We'll make our planks slightly longer than that. Let's go with a height of 0.1 and a width of 1 meter. Let's make it 8.1, just a hair wider than the bridge itself. Then enable scaling. Then have it follow the curve to drive the f-axis. You can also assign separate attachments to individual planks like independent ropes or specific props sitting on certain planks. Once the planks are set up, you can place these unique objects. They won't show up before the planks are defined. By putting in space-separated paths, you will pick one at random. You can also insert an empty asset path. If you leave an instance path blank, that plank will be treated as missing. This is great for creating broken or missing planks, and you can control this using a probability slider. For instance, a 1% chance that a plank is missing or broken. You can adjust the thickness of the bridge towers here. And this handles the overall global vertical offset. Let's pull up a JSON project file I worked on earlier. This is the exact project setup I used for Skull Island. These points here represent the nodes formed where the horizontal and vertical ropes intersect. The rope nodes are also specified right in this section. Once the JSON file is imported, you can tweak parameters like length and slope to fit your scene. I'm just doing a quick rundown here. After changing parameters, you can export a new JSON file. Let's take a quick look at the help documentation. Now let's talk about exporting. We'll merge the terrain and the scattered data together. We already showed how to convert the terrain into 32 layers. As you can see, we have exactly 32 material layers from layer 01 to layer 31, and all the other useless layers have been trimmed out. Merge everything you want to export together. You can run these nodes directly inside UE or Unity, but since the CNI build is massive, it can cause severe viewport lag. During testing, I found that the most stable and performant method is exporting as a geo file. Drop down the file none. Set the action to write. Pick a path and export it out. Awesome, export successful. Once it's successfully written out, you just need to load this file into UE. Now let's go over how to load that exported BGEO file inside Unreal. First, head over to the QuickBrush toolkit, open the Autos folder, and find load_bgeo.hda. Drag it right into our content browser. Let it load into UE. Next, drag the node into the scene. It comes with a default coordinate, so let's zero it out. Right now it's grayed out because the Houdini session isn't running. Let me quickly restart it. It turned yellow, meaning it's paused. I have it set to pause by default, so let's unpause it. Now it's green, which means it's live and running. Click right here. And let's load the map.bgeo file we exported earlier. This thing takes about 2 to 3 minutes to fully load. Alright, loading is done. I've actually imported this scene once before. For a brand new scene, you'd need to locate the river material and reload its new flow map. Because the flow map might have changed. Since this is a geo file I exported earlier and none of the parameters have changed, I don't need to redo those settings here. And that is how you load a scene using LoadGeo. Once it's fully loaded, if you need to bake it out, just click Bake right here to completely convert it into native Unreal assets. And here are the towers. Over here is the missing plank we set up. That's pretty much the whole workflow. Next, we'll talk about scattering points along a curve, which can be used to create fences, railings, or to scatter gravel. Here, I've drawn out a curve. Let's add a curve scatter node. Feed the curve into it. Add a scattering rule. It defaults to biped, which handles the number of repetitions. It looks a bit small. Let's upscale it so it's easier to see. It hasn't filled the line completely. If you check Allow Adaptive Scaling, it will fit the curve perfectly. There are 3 scatter modes in total. The first is by count, meaning how many total pieces of the current object to place along the curve. The second is biped, which controls how many pieces it places at once whenever this rule is triggered. And the last one is by percentage, which dictates the probability of an object spawning when the rule is called. Let's look at this option first. It toggles whether the up-axis aligns with the curve or just points straight up. Let's add another rule and bring in something a bit larger. Tweak the settings a bit. Switch to backcount mode. It only places a single piece because the count here is set to 1. No matter what number you input here, it will distribute them evenly along the curve. Because this rule has up pointing straight up, checking this box will reorient up to face the curve. You can set an offset value here. Say you absolutely need a door placed at a very specific spot. If a gate must appear right at the start or dead center, this is how you configure it. If you leave this unchecked, the current object won't be allowed to scale. It will just sit rigidly at that location. Generally speaking, when you're placing modular architectural pieces along a curve, at least one of the modules needs to allow scaling. That way, it can seamlessly stretch to fill the entire curve length. Otherwise, you might end up with gaps. Of course, there's an exception to this. If we check is first and is last, the very first piece will always be forced to be this specific module. If you leave them unchecked and use by count to place 3 pieces, they will just space out evenly along the curve. But if we check the first or last slot, it will spawn 2 extra pieces, and this won't override the number you set in by count, meaning you'll get 5 pieces in total. This saves you from messing around with manual offsets. If you already have 5 pieces here, but try to force offset it back to the starting position, you'll end up with a double stack somewhere. Reversing the direction does the same thing. You'll get 2 pieces overlapping right here. Now let's look at something pretty unique. Say I absolutely want a secondary attachment prop to sit on top of this model and constantly follow it. We can use add attachment here. Add an attachment. I'll anchor it directly onto this model. Center it on X, snap it to positive Y at the top, and center it on Z. This will place an attachment right on top. On top of that, you can still apply offsets to fine-tune it. You can also inherit rotation and scale. It won't look any different in the viewport display here, but once exported, it will inherit the scale and follow along. Just a quick demo of how that works. You can stack multiple attachments on a single piece as well. Let's do a quick demonstration. And there you go, an extra attachment asset is added on top. This system supports preset template loading as well as parameter template exporting. For the detailed underlying logic of these parameters, you can consult the help documentation here. Let's say we want specific flanking assets placed on both sides of an object. First, insert a scatter rule right before this. For rule number 3, we place 3 items, so we'll have this one place 3 items as well. Using count mode, let's dial in the parameters. Have it use the curve to drive the up axis. Then add another rule right after it. Tweak the values. Also set to by count. This guarantees that it will always be flanked by 2 companion items on either side. This one is out, and that one is full. Let's adjust the alignment axis and offset values. But this issue won't pop up on the outer edges, because we only configured 3 instances. If multiple objects have its first or its last checked, the system will only recognize the very first one in line and ignore the rest. This is perfect for setups like doors or railings where the end pieces require custom handling. Now, let's talk about the placement by probability mine. Let's add one more rule and adjust the parameters. This time, we'll use by percentage. This makes it spawn based on a probability curve. Let's play with the values to see how it looks. Setting it to 100% acts exactly the same as repeating it once. That's the basic idea. Feel free to experiment with it. Let's circle back briefly to the terrain material. For the terrain material, we utilize the landscape layer blend node. Inside this node, we map the attribute names to match the layer array from 0 to 31 that we generated back in the Houdini environment. This is just what I've built out so far, roughly 7 or 8 layers. To separate blend outputs feed into the base color and normal maps. It's a pretty straightforward setup, mostly just for demonstration purposes. We're using world position coordinates here to act as the UV mapping. And that's pretty much what it looks like. On top of that, there's a water material we need to talk about. For the water surface material, I set up a flow map. The logic for the flow map looks roughly like this. It's calculated exactly this way inside Houdini, and then we map it back. Grabbing the tangent vector. And that's about it.